to again give a talk here. It's always really very, very nice to be back here. Okay, so I'll be talking on null fluids. This is something that I'll define what it is, just a name for a particular theory that I'm going to describe. Whereas the other part of the title is familiar, and that is I'm trying to tell you to look at Galilean fluids from a new perspective. Okay, so if some of you are not familiar with Galilean fluids, I'll go ahead and tell you about that. Okay, so before I start, I should just mention that this talk is done with, the most of it in these two papers that I'm done with Shubham Bagato and Akash Jain. He's a faculty member at IISER Bhopal, and Akash is a graduate student in that. So that what really is not very, very technical in that sense. Good. So, being a graduate student, I myself was not very much familiar with all the technicalities, and if a graduate student can perform it, I would think that it's not that.
No, the calculations Shantini performed, which is
but that's a technicality. That's a technicality at a different level. That's a technicality at a different level. But not really. My point was you really don't need to do lots of string theory and differential geometry to do this. That's it. Okay. So motivation. Why I want to do this? So again, it starts from the very basic fact that first of all, fluid dynamics is certainly not a new subject. It's a very old subject and mostly developed by Null. But relativistic fluid dynamics has been revisited a lot post 2006. And the main reason why it has been so is because the interest started with some non-trivial results that were found based on holography. Okay? But later on, so of course the trigger was some results from holography, but later on people thought that maybe some calculations and again some relooking at relativistic fluid dynamics is interesting. So people started working in fluid dynamics itself, not with connection to holography. Okay? And then some major results followed from apparently to different physical constraints on relativistic fluid dynamics. And those are by first locally imposing a second law of thermodynamics. This is, I'm not really describing a lot because most of all these things have been developed here in TR for itself. But if any of you want to know more about it, I can tell you. So first is by locally imposing a second law of thermodynamics, and this was done during 2009 and 2012. And then by finding an equilibrium partition function to constrain the dynamics, and that was done in 2013. And later on, actually it was shown that these two apparently different physical constraints give similar kind of restrictions on fluid dynamics in 2014, and why that should be the case in that was understood. This is Shanghai's. So, and then came the last blow that I find really interesting, and this is done again by someone from here, Nabamita, with Mukund and his student, where they have been able to classify all the transport coefficients of relativistic fluid into 8 different classes. Okay, so that has been a really very nice result on relativistic fluid dynamics. So after saying all this, actually we can assure ourselves that lots of relativistic fluid dynamics are now under control. Okay, so people have good understanding of how things are going over here. And this success also gives us a new question to ask, and that is, what about non-relativistic fluids? Okay. Can we also construct some partition function for them? Can we also classify all the non-relativistic transport coefficients into some classes like the relativistic one? So, what the question that I want to ask is, like the relativistic fluids, can we also give some more structure through non-relativistic fluids? And that is why this is what motivates me to study again the non-relativistic fluids, although it is very well developed, well known. Okay? So I must say that the study of non-relativistic fluid is certainly not new. After the success of relativistic fluid dynamics, just in 2008 and 2009, this study was also started again by Mukund, Rangamani Ross, and Harzov. So they started the study, and as I will go ahead in my talk, I will try to tell you starting from here, where have we been able to reach. Okay?
I'm really sorry to preempt this, but just simply speaking, isn't non-relativistic fluid motion a subclass of full relativistic?
Why don't you just wait? The answer is no. The answer is no. Okay. Fine. So, after giving the motivation, let me tell you the plan of the talk. So, the first part is motivation that I have tried to give you. And then I will talk about how to get a non-relativistic fluid. The idea that I will follow is null reduction. I will tell you what that is. And then I will talk about null reduction of a relativistic fluid, and I will tell you why that doesn't work. And then comes null fluid, the theory that I want to talk about, and the proposal and outcome. And feel free to stop me at any point. Okay? So is the question clear? Do you understand a bit of relativistic fluids? Now let's go ahead and try to ask the question for non-relativistic fluids. Okay. Now you can also stop me at this point itself and ask me why do you even want to do that? Because there the motivation was like holography was telling you a lot of stuff. Here, why do you want to study non-relativistic fluid? If any of you have that question, I'll answer it at the last. Okay? But let's, for the time being, just take it and go ahead. Okay. So what is a non-relativistic fluid? So relativistic fluid is something that all of us know by now well. If some of you are not much familiar with non-relativistic fluid, let me just tell you in one slide what they are. Okay, again, these non-relativistic fluids, you can also think of them as some low energy fluctuations around the thermodynamic equilibrium of some theory that has Galilean symmetry, the non-relativistic symmetry. Okay? And they are also described by fluid variables, that is some velocity, and now two thermodynamic variables. This is something that you can find just at the first page of Landau equation, how to describe non-relativistic fluid. Okay? And then they are characterized by Galilean currents and densities. These are the densities, and these are the currents, and this is the stress tensor. And these quantities satisfy these equations.
Epsilon is the energy density?
Epsilon is the energy density.
Rho I think of as like a number density.
Yes, rho is exactly the mass density. So first equation is nothing but an energy conservation equation. Second equation is nothing but a continuity equation. And third equation is the momentum conservation equation, which also has a different name for the equations. So when we talk about relativistic fluid dynamics, all we talk about is basically how this equation, how these guys are evolving with time. And exactly like in relativistic fluids, even here,
Rho J is the number density flux.
Yeah, kind of you can think of it being a mass current, number density flux. Yes. And this is the energy density flux.
Sorry, the last equation.
Last equation.
That F is equal to ma somehow?
That's what?
Sorry, please explain that last equation just once. The Tij was what?
This Tij is like the stress tensor.
So it's like momentum.
It's exactly the momentum.
I'm not understanding how number density is related to momentum.
No, this is the J, the current.
The current of number of molecules or
Yes.
mass of molecules?
Mass of molecules.
Okay.
So this rho J is actually nothing but rho times Vg.
Vg, I see.
Yes.
Thank you. So that's just the moment, that's Newton's law.
Yeah.
Where was you at?
Yes. So now these currents and densities are actually functions. So you see, we have like these 5 quantities here, but all of them are functions of fluid velocities at the 2 thermodynamic quantities. Okay, so that's what is non-relativistic fluid dynamics at the very basic level.
So low energy fluctuation, low energy compared to what?
It's like exactly if let's say I have a field theory. Which does not have, instead of it having the Poincare isometry, it has some Galilean isometry. So it has some energy scale of it, and then I am giving it some fluctuations, which the fluctuations are such that you can think of it being at equilibrium at every space-time point, and then I am just varying it by very small. It's exactly, the idea is exactly, I would say this was probably the first step, and people actually extended this to relativistic fluid dynamics. I'm just trying to tell it in the reverse way.
So low compared to mean free path and a mean free time.
Exactly.
Basically. This equilibration length scale and equilibration time scale.
No, but amplitude can be big, right? Your distance scale over which things vary have to be long compared to mean free paths.
Yes.
So the amplitude, the size of the water wave can be very big.
Yes, because
right?
everything is function of space-time. So
So in
that
that sense, it's not low energy compared to anything. It's just long distance and long.
I think relativity means time, low time there.
low time.
That's
So
right.
basically, it means that I can expand everything around the equilibrium in a derivative expansion.
That is the same for relative.
Exactly. Exactly. But the difference is here, you see, there in relativistic fluids you have a certain equation, that is the stress tensor. Let's just take the easiest case, and then the equation is del m of Tmn equal to 0. There we express everything in terms of fluid variable, that is velocity and temperature. Here the difference is, these are your equations, the densities are these guys, and the variable is again the fluid velocity, non-relativistic velocity, and 2 thermodynamics.
But I mean, the velocity should be less than the speed of light.
Exactly.
Right?
Exactly. So these currents and densities are functions of fluid variables and can be written in derivative expansions. Okay? Fine. So this is what we want to describe. Now the question is, next question to ask is, how to get a non-relativistic fluid? Theoretically. Now there are 2 ways to get there. First is something that Shanti was telling me, that just take a relativistic system. Let's not say fluid. So take some relativistic system and take the C going to infinity limit of it, and you can think of the, if you are lucky, you can get the resultant system to be a non-relativistic, to be a system that will satisfy, that will have some quantities which will satisfy this equation. Okay, so that is one way to get there. Another way to get there is by studying a fluid system that obeys Galilean symmetry. It's exactly again in the line of relativistic fluid. There is try to study a system that has Poincare symmetry. Now we say that let's have a system that does not have Poincare symmetry but Galilean symmetry. So of course that is a non-relativistic system, and let's try to see if I can get the correct equations from it. Now the first one actually is a subclass of the second one. Why? Because in the second one we are allowing all possible terms allowed by symmetry. Now it is possible that some of those terms are actually 0 when you are taking the C going to infinity. Okay, so the first class, you can, I mean, if I study the second class, I am certainly starting the first class, but not by symmetry.
Well, but if you allow the C goes to infinity limit in the most complicated sense, and it's still really true that the second one is a subclass of the first, then for the real world only the second one is relevant. So the real world is a low energy limit of a relativistic thing.
Yes.
So this anything that's, I mean, are there really genuinely things that are in the second class that are not in the first class when you allow the most complicated thing?
If I believe on some papers.
But just if that were the case, you would be saying that there is a restriction on low energy physics from the criterion that it is at arbitrarily high scale relativizable.
Yes. So
it should be a very interesting statement.
No, I'm saying that some people. Some people have done some calculations taking C going to infinity limit of some relativistic fluids, and there they are not able to find some transport coefficients that are actually allowed by the second process. But it is also possible that the second process is giving you a transport coefficient that if you can compute it on a model and then really take C going to infinity limit, that term will vanish. It's possible. But okay, first of all, for that I need to make sure that the way they have taken the C going to infinity limit is correct, which is not always true.
And it's the most general way to do it.
Exactly.
That is the
yes, because taking C going to infinity limit is not an easy thing to do.
Like the ones that Shiraz and Sveta and Sandeep also have done, in that, you do this in a way that the scaling between the space and time are different.
Yes.
So one is quadratic and
yes.
other is linear.
Yes, and you need to also scale different quantities in your theory with C to make some sense of the limit.
For instance, you may want to scale a chemical potential in a particular way to make sure that's tough for me.
Exactly.
So
exactly.
You
have to
look
do
at all
it
possibilities.
Yes. But at least so depending on all possible ways, actually, at least for electrodynamics, it is known very well that there are 2 theories when you take C going to infinity. Starting from a relativistic electrodynamics, you can get 2 different relativistic electrodynamics by taking. One is called some electric limit and one is called a magnetic limit. So that kind of.
Just think of it in a different way. From from the Poincare algebra, is there different ways to take the...
Yeah, I'll come into that. Exactly.
Sorry, let me just say again. But if you can show that there is a term in a Galilean, anything that obeys all your constraints but can never come from a parent relativistic theory, I think that's a very interesting thing.
Yes. So
because it suggests that there may be constraints on condensed matter physics from the fact that the real world is relativistic, no matter how far away. Sounds unlikely to be true, but sounds very interesting.
But okay, so first of all, the first statement is taking C going to infinity limit of a relativistic fluid.
Yeah.
Because that's what people would think, and all. Right. I have a fluid and I take this limit. I should be able to go to the non-relativistic case. So let's see what that do for us. And then the second way of looking at it is basically again let's study a fluid that has this symmetry, that has lower symmetries. Okay. In the rest of the talk, I'll be talking about the second way of looking at Galilean symmetry, but I'll make some comments about the first. Okay. So now the question is that so we understand how can we get a non-relativistic fluid. So the way that I'm going to follow is to try to build up a system that has Galilean symmetry. The next question is how can I write a theory with Galilean symmetry? Again, there are many ways possible. First of all, you can just from the very beginning try to construct a theory that does not have relativistic symmetry but Galilean symmetry, and that has also been done by some people in the context of fluid that I'll comment about at the end. But I'll take again a little different method, and that starts with a fact. The fact is, we all know, if some of you are not, you don't know about it, I'll tell about it anyway. So the fact is, the 4-dimensional Galilean algebra is actually a sub-algebra of a 5-dimensional Poincare algebra defined as the subset which leaves a particular momenta, which is null, invariant. Okay? So what does that mean? That means let's consider a theory in 5 dimension which has Poincare, satisfies Poincare algebra. Okay? So you have translations. The Poincare generators have translations and the rotations and boosts. And let's take the indices to run over 5 directions. And you know the Poincare algebra is just this. P with P is 0, P with M is bunch of P's, and M with M is bunch of P's. This is my Poincare algebra. Good. Now, define these coordinates. So, out of xm, I am defining a x plus minus and xi such that x plus minus is nothing but a flight form combination of x0 and x4. So, this combination, and ij are just running over the rest of 3 values. So, suddenly now Pm will have 3 pieces, P plus, P minus, and Pi. And M's will also have these 4 pieces, M plus minus, N minus I, M plus I, and M minus I. Now let's just pick up a subset of these 7 kind of generators, and that consists of P minus, P plus, Pi, M minus I, and M I. Now one can show, as I'll show in the next slide, that these guys actually they have an algebra, a closed algebra, where P minus acts as a causal. Okay, so what do I mean by that? So the P minus, let's define Mi minus to P minus, and then you can show that P minus with P plus is this, Pi with Pj is P minus, so that's the central extension of your algebra, and other guys are exactly same as they should be. M with P is P, M with P is B, and M with M is M.
I'm sorry. Is it the only way to get a Galilean algebra from the Poincare algebra? Is it the are all Galilean subsets of the Poincare algebra something that leave a null momentum invariant?
Yes, that will give you if you start with the Poincare algebra with that condition, then that will always give you a Galilean.
But are there other ways to get it?
Of course, you can try to take the C going to infinity limit correctly. I mean, wrong.
Okay, so what I'm worried about is what is the physical interpretation of the fact that you're leaving this null momentum invariant?
Yeah, just wait a minute. I'll talk.
Okay.
So at this level, I'm just saying what happens at the level of algebra. Okay. So at the level of algebra, we can see that if I just take some bunch of it, they certainly closes among themselves with the central extension and gives us Galilean algebra, where you can just identify all the quantities with Galilean generators as P minus to beta continuity quantity. The time translation is the Hamiltonian is P plus, space translation is Pi, Galilean boost is Bi, and Galilean rotations is N.
So is it like you are going to say that P plus is going to be some pi divided by twice P minus, and therefore
P plus is independent.
No. Let's say you took a relativistic particle, okay, and you do just like people do in light from QCD, and like reactions that take you to the discrete light from quantization.
Yes, this is nothing but discrete light from quantization.
So
but I have not yet gone to the level of quantization. I'm just saying what it does at the level of algebra.
But you are going to identify eventually this, Hamiltonian equal to P square over 2n. Instead of that, you are going to have P plus is equal to P square divided by 2P minus. And that you are going to, anyway, carry on.
No, I think at this moment, this is just an independent, this is completely independent of that.
She's not going to look at single particle.
Now, just to put it in Nabamita, you said continuity, but equivalently, if I'm right, you can think of this as the mass,
Exactly.
right? So P, which is
This
what
is the, exactly.
Yeah.
That's
one of the additional equations you had was
exactly. It's just the central axis. So to again tell you absolutely correctly, if I set P minus to 0, then the algebra that I get is the real Galilean algebra. This is a centrally extended Galilean algebra. It also has a name, Parchment algebra, that I got to know after I wrote the paper. But that's what.
okay. So the traditional Galilean
Algebra is
minus equal to
0. Yes, that is Galilean. This is centrally extended.
The traditional Galilean algebra is one which has been constructed by some contraction, or
No, traditional Galilean algebra means very traditional.
Not someone like me will know, not someone like you.
Like, when you say about Galilean algebra, your generators are basically translation, boost,
It's just like
integration, and
a
Hamilton.
boost and a translation, they commute with each other.
Exactly.
But
That's what is the
there
tradition.
was by Rajesh where they had scaled and then did some.
Yes, right. The way to see the Galilean. Yes. So here I'm just saying that I'm trying to get that. I mean, I'm not trying to get. This is a very, very well known. I said that this is a fact. Okay. So I'm just restating it for some of you. If it is not familiar, that this is a way how you can get Galilean algebra from Poincare. Okay. So what is the lesson from this? The lesson from this is, if we start with a relativistic theory. Now I'm going to theory. Okay, that means a theory with Poincare invariance, and then define a null direction, and then reduce the theory over a light cone with the null direction. We end up with a theory that is not relativistic, that is which has IISER invariance and Galilean invariance, but in one lower dimension. Okay, because you recall in this process, all I have done is from 5 coordinates, I have been able to go to 1, 2, 3, and my x plus is there. X plus is like time, so 4. I started with a theory in 5 dimensions with Poincare invariance. Then I said that there is a particular direction which is completely, all my fields are completely blind to that. So my fields are independent of that direction. And then you can just reduce your theory on that direction. If you choose that direction to be a null direction, yes, if you choose that direction to be a null direction, then the resultant theory has Galilean symmetry. Okay, so that's the lesson from these small exercises. Okay, clear? Okay, so the next and most straightforward task would be to apply the above procedure to relativistic fluids to get non-relativistic. Okay, and this is what was done by Mukund, Ross, and Harzog in 2008 and 2009. So this is the starting point of studying non-relativistic fluid dynamics afresh. Okay, so people try to start with a Galilean fluid and then define some null directions and reduce and then say that all my fluid variables are independent of x minus and reduce the theory on x minus and see what they get.
So that's effectively a null reduction of the hydrodynamic equations.
Absolutely. That's exactly what I'll do. Okay? So let's see what does that give. Again, and let me start with the relativistic ideal hydrodynamics. All of you know it. So these are just given by some conserved currents for the most simplest possible case, where you don't have any charges and no anomalies certainly. So the equation is just the conservation equation of stress tensor. you see this is like if your space-time dimension is 5, you have 5 equations. So I need those many variables to solve this equation. And the way one chooses the variables for relativistic fluid is temperature and velocity, such that velocity is normalized. So you have 4 plus 1 5 variable. One needs to write. Does not need to, but if you aim to solve this equation, then for fluids, TMN should be expressible in terms of these quantities. And the most generic possible expression that you can write at 0 derivative level is this. It is a symmetric tensor made out of your variables. So possible thing is UN. This is symmetry, and a metric that you can have. Here I have also taken a metric to be flat, to be at a very decimal. Okay, now the coefficients are certainly arbitrary, and they are dictated by the thermodynamics of your system. Here particularly this E is nothing but the energy density, and P is nothing but the pressure density. Okay, so the fluid is required to satisfy the second law of thermodynamics locally, and that just means that you should have an entropy current in your picture that should satisfy this condition, that the divergence of the entropy current should be always positive, definite. And that says that again, this being a vector, I can choose it to be some coefficient times the velocity. That's the only vector that you have. And if I demand that del m of Jm satisfy this condition, then that requires these two guys, and this to satisfy these conditions. And you can just look at them and understand that these are nothing but a thermodynamic equation. This is the first law: dE equal to temperature times Ts. Where S is the entropy density, and E plus P equal to theta times S, which is the Euler equations, or Gibbs equation. Okay, so this is relativistic fluid. Again, now very simple. Okay, so now the idea is, let's apply the earlier procedure that I just described, the procedure of null reduction on it, and let's see what we get. Okay. So for simplicity, let us consider, as I was doing, flat space. So the equation is just del m of TMN equal to 0. And now if you perform the null reduction, like just define x plus minus out of the two coordinates, then you can rewrite this equation. You suddenly get three kind of equations from here, right? When the free index is minus, when the free index is plus, that I am calling to be t, and when the free index is some j. So there are three kind of equations. And they can be realized, actually, the continuity equation, the energy conservation equation, and the Euler equation of non-relativistic fluids. If you identify rho with T++, just, let's go back. Yeah. So you have these three sets of equation. All you need to do is just restating. Okay, I had them completed here. So if I just re-level T minus T plus T as rho, Ti as rho I, and for others, then these three equations are nothing but these equations. So this is what was done by Mukund and Cross and Thus. So now, since we know what T++ is, because this is nothing but the T++ component of my relativistic fluid, so I can actually go ahead and write the dictionary a little more precisely. So T++, rho is just T++, which is R is nothing but this combination, and similarly for other. I'm just trying to say that I can write all non-relativistic quantities in terms of my relativistic quantities. So in that sense, if I know the relativistic fluid dynamics, then I know everything about the non-relativistic fluid dynamics. That is what was their idea.
It was R defined before, or is that the basis?
This R is nothing but this combination. These guys are defined before, instead of writing it. Okay, so we recover the outcome is we recover the standard constitutive relations of it. Okay, so they started the discussion and they ended here. And then suddenly people tried to understand what happens if I go away from the ideal fluid consideration, what happens if I take charged fluids, and so on and so forth, and problems started coming up. Okay, in fact, the thing that we were trying to do the same analysis for charged fluid. Suddenly Landau doesn't talk about charged non-relativistic fluid, so you need to write all the constitutive relations for them. You need to put conditions on it by constructing the entropy current and calculating its divergence. And the results that we were finding is starting from a generic charged relativistic fluid, we were not getting a generic charged non-relativistic fluid. So what can be the reason behind it? It was not clear to us at that point.
Following null reduction.
Following null reductions. Okay, so let me write the result. The result is, so charged relativistic fluid. If I do null reduction, I get a class of charged non-relativistic fluid. And that was already, one also did this by taking C going to infinity limit. That was already a subclass of this. So they didn't have some coefficients. Now I don't know their way of C going to infinity limit, how correct is it. But whatever they did, if I follow that, they were not getting the coefficients that we have. Okay, fine. But what can we, but this is certainly not what we want. Right? What would be the reason for something like that? Actually, when we tried to understand the reason behind this, we understood that the problem is not at the level of derivatives or introducing other fields. The problem was even at this level itself. What is the problem? The problem is, okay, we see that the constitutive relations are working, but what about the thermodynamics? Okay, so relativistic thermodynamics was just this, that dA equal to theta times ds. Let me just put a rel. It and E plus P was theta times S. If I just rewrite the same equation in terms of my non-relativistic quantity, then I see that the equations that I get are these. dE turns out to be proportional to two quantities, dr with a coefficient and ds with a coefficient, and E plus P again turns out to be a sum of two quantities, something with proportional to R and S. So from here it is very easy to identify this should be the mass chemical potential and this should be my temperature, non-relativistic temperature. But this is true only up to this condition. Why? Because we saw that this R was satisfying this. This R is nothing but I identified this big quantity with R, and then R is restricted. Okay? So this relation is equivalent to this relation. So all the null reduction of a relativistic fluid is doing for you is, it is giving you the thermodynamic quantities not as a variable of, not as a function of two variables, but as a function of one variable, which is in some sense expected, because in relativistic theory that's what it is. In relativistic theory, all the fluid only thermodynamic variable that appears is temperature, and everything else is just function of one variable, and that's what is showing up even after the null reduction. Okay, but this should not be the case for a generic non-relativistic fluid. For a generic non-relativistic fluid, all these quantities, everything should be function of two variables, temperature. I chose them to be temperature and chemical potential. You can choose them to be anything. For example, Landau chooses them to be the density and the volume. Okay? Right? So, but the fact is the number.
You're starting from a higher dimensional system, and you're taking one direction of the momentum to be your particle number. So the higher dimensional Lorentz invariance related what was happening there with what was happening with energy momentum, and that's the reason you had one variable going to two, right?
Right.
So, but if you started with a higher dimensional system where you genuinely had two different things, like energy as well as a charge.
Charge? You mean yes?
Not a null reduction.
Yes.
So it's just C goes to zero. C goes to infinity.
Yes.
You start with something which a higher dimensional system where you have really energy as well as a charge. So then this higher dimensional theory will also be characterized by thermodynamics as a function of two variables.
Right.
And that could more plausibly give you the general thing.
That's what null fluid is. You already got the answer.
Actually, why even start from higher dimensions?
It's not the relativistic theory.
Yeah, that's right. You
Yeah, see,
do the relativistic theory. The question we are asking.
Yes, I'll come to that. So this our work is 2015, and after we realized that there was some problem with null reduction of a relativistic fluid to get non-relativistic fluid, people understood that that's not really going to work. So we need to think about some new way to get non-relativistic fluid, and that's where Jensen started. So Jensen did this work around 14.8, where he was trying to construct a Galilean theory, a relativistic theory in d dimension itself with these two possibilities. Okay, but I'll tell you what exactly they face if they do it. So all I'm trying to tell you now is that there is a consistent way. So here we understand that if I start with null reduction, which is a right thing to do if I want to get a theory with Galilean invariance, then and apply it to relativistic fluid, it does not give me the generic non-relativistic.
And as you said, now that you said it, the fact that it was a function of one variable already told you right from the beginning.
Yes, right from the beginning it would have been very clear, but apparently it was not clear until unless we face this. Okay? Yeah.
I'm sorry to ask such a remedial question, but
Is that appropriate for us? Can we have it?
No. Take a new one. Who knows?
Yes.
Sorry to ask such a remedial question, but just from the point of view, not extra dimensions and so on, but just the point of view of taking the relativistic equations and taking the non-relativistic limit in, say, a fixed number of dimensions, you have one more extra equation in the non-relativistic case, right?
Yes.
Which is the mass conservation. And just
Not this one. I mean, in that sense, basically, yes, you start with del m Tmn equal to 0, which are 4 equations. And now if you think of one of them being T and the others being 3 spaces, then this is like 4 equations. Here you have 3. Yeah. 3 plus 1 plus 1, 5 equations.
Yeah.
Yes.
So you have one more. And what happens? Presumably the energy conservation equation in the relativistic case breaks up into 2 equations, right? To 0th order energy is just mass.
Yes.
And so that gives you the mass conservation. But then when you keep the V square correction to energy, then that gives you the energy conservation.
Yes.
Is that right?
Yes.
So that one equation actually gives rise
Yes,
to
but again, I mean, when some people were trying to, the way Jensen was doing it, he was not really trying to play with the relativistic fluid equations to get the non-relativistic. Even that would not work, even if you are not changing the dimension. Just being the fact that there also every quantity would be just function of one thermodynamic variable, and that will not give me the right Galilean. Okay, so the way he was trying to,
Why is that? I mean, isn't it that one equation seems to give you 2 because mass is independently conserved? I mean, if you take the non-relativistic...
It's not so even here if you notice, the equations are not the problem, right? You get the right equations. The problem to see their structure, what their function.
Here you started with one more equation, because you started in 5 dimensions.
Yes.
Sandeep's asking, how do you start in 4 dimensions, start with 4 equations and get 5?
Yes, I understand his question, but I'm saying, so you are trying to understand that you can get equations, but why there is still a problem. So I'm trying to tell you, first answer you that even if you get the equations, the fact that all these quantities are functions of one variable doesn't change.
But just to go back to what I thought he was asking, suppose you don't do this.
Yes.
When you start in 4 dimensions with the relativistic theory, you have 4 equations.
Yes.
Now, how will you get 5 equations starting with 4?
Yeah, okay. So for that, what you need to do is basically, so that is what has been done by some people again, Cummins et al. So there you need to scale again. Okay, so let me start with the equation. Again. 0. 4. The first thing that you need to do is scale every quantity properly. Scale all variables. We'll see. Okay. The temperature and fill variables. We'll see properly. And then expand this equation in power C and try to set them to 0 as in power. So this equation, now when you break the equations, it sometimes will go as 1 over c, sometimes can go as c square. Then you set the coefficients to 0 and you get.
I think that's right, because u0, which is square root of 1 minus v square over c square, when you expand that,
yes.
The first term is 1, but then you have to keep the v square
So
over
there
c
you
square.
need to expand things, you need to look at things at power sensi and then set them.
That's right. But if you do that, I mean, then as you say, you'll get 5 equations out of 4.
Equations come.
But what then is the problem? Thermodynamics certainly has to work. Gibbs and him, etc. will not fail.
Yes.
So
see, let's again start from this. You have E plus P equal to T. Let me write temperature T times T and dE is equal to T times dS. Okay. Now, and all these quantities are basically we look at them as being function of t. Now when you are expanding this guy, you suddenly get some E plus P equal to again some T subtimes this. Right? And this equation also, so now these are, let's say these are relativistic, and you get something non-relativistic. That's what they got. Okay? E relativistic or 15 times plus null. But that's not the thermodynamic equations of a Galilean system anyway. So the thermodynamic equation of a Galilean system is you need something else there and you need something else there. The way they did it,
because you have an extra charge.
yes, you have this mass chemical potential. So you should have a mu m times r here.
Okay, but then in the relativistic context, what is this charge? Not from a higher D point of view, but just from the 4D relativistic system, do you have an extra charge in that theory?
No.
Because
So you have an uncharged fluid which is moving around. It does have to zeroth order some mass density.
Yes, and so when I'm talking about these relations for Galilean fluid, that is just uncharged Galilean fluid. You don't have any charge there.
But the mass term we are writing down here
This is for Galilean fluids, huh?
for a Galilean
Yeah,
fluid.
this part is what you get from a limit of a relativity.
But it's not the case here that if you look at energy to zeroth order its mass
So-
plus the non-relativistic energy is like mv square. So
But
the two
that-
terms combined.
So the point is that the thing that I'm trying to tell you that there is a new variable. How are you going to get it from?
But why do you have a mass because of this? You have a mass because you've got some conserved baryon number or something like that.
Yes.
So the fact that there was this mass was the fact that there was an additional conserved charge in the relativistic theory and you're working in some sector of that. So that has to go, that information has to go.
That information has to go. So that is, so now, okay, after understanding this, no, since you asked. I came here not just to give the seminar. So the idea is what Jensen now tried to do is so he started with these equations, which are Galilean, and then tried to write them in a covariant way, so that it looks like a kind of a covariant system. Whose if you take the I and T components, then you get these equations. Okay, so it is not a relativistic system. What Jensen was doing is basically, so what he did was basically rewriting the Galilean fluid equations in a covariant way. Okay? So by having the Galilean diffeomorphism intact and by hand imposing the Galilean boost invariance. So that's what he was doing. Well, I don't. Maybe someone can actually write things just starting with a theory with some additional factors into it. But to me, it seems that I wouldn't do that. I'll just follow null reduction because it's much easy.
No, that you might want to do, but the question is in principle whether you can get something else.
Yes, I understand your point. So to get something else, you have to start with something else.
Sir, this mass chemical potential is not there in the relativistic case because mass and energy are interchangeable, right?
No, but even in the relativistic case, you have to say that you're starting with a certain number of atoms.
Yeah.
You can start with different numbers of atoms. So that's but it's a super selection. Yeah, I mean it doesn't. Yeah.
I'm assuming it's a particle chain sort of process, I guess. Like so something heavy can split into two light things with a lot of momentum.
Yes. I think if you started with a fixed number of atoms and you kept them fixed all throughout, you may not see that mu r term just because it's a fixed term. I mean, you can put it into your energy, fixed constant energy, right?
Yes.
And so on. But yeah, otherwise you would see that term,
Yes.
and then it should match up in some way.
Yes. So the point is, nobody told you that what should be the variables to start with. Just because I thought that I would start with the relativistic fluid dynamics and then I know how to handle and how to deal with that, so I knew what are my variables. And the result that I'm seeing is if I start with that, then I don't get this anymore.
Right.
Sorry, my question was slightly ahead. Suppose you had a sort of relativistic fluid dynamics in which mass and energy are interchangeable. So suppose you have heavy particles decaying to light particles with a lot of momentum. But then in the non-relativistic limit, you still see the mu m r term.
What is the mu? I mean the parent of mu and r term in upstairs?
Just the fact that
No, that fact quantizes. In terms of quantity, that is what?
It would have to be some conserved charge. Because otherwise, these heavy guys would just decay into the light slip. Something has to protect them.
Okay. You wouldn't have a limit where you get some net residual matter moving slowly.
Sorry. Yeah. So you said one quick question. You said C going to infinity limit actually gives the subclass of fluids obtained from the null reduction. Does it have to be a subclass? Means is it a coincidence or
no?
Because
See, in the case where I know the results, it is a subclass. That's my statement 1. My statement 2 is, if you construct things which is satisfying some symmetry, just symmetry is your guiding principle, then you will write all possible terms allowed by the symmetry. Right? Now, it is possible that coefficients of some of these terms can act, and when you are computing on a model, can go to 0 when you are taking C going to infinity. So some of these coefficients can actually vanish in the C going to infinity limit, but from symmetry principle, you will allow all of them.
No, but null reduction was just one of the ways, right? It wasn't.
Null reduction is a way to is a way to break your symmetry.
Yeah.
So I'm saying now, so if I start with a most generic fluid allowed by Poincare symmetry, then by doing this, I get a most generic fluid that can have Galilean symmetry. So it will have all possible terms that are allowed by symmetry. It is possible that some of these coefficients can actually vanish when you take C going to infinity. And have nothing to do with the symmetry.
So if you start with the high dimension theory, we even have conserved charges. So can we get all these things like space?
I'll show you. Yes. The answer is yes. Okay, but is it clear? Up to this point, we have understood that null reduction. First point, that null reduction is a good thing. Is able to take you from a relativistic theory to a non-relativistic theory, point 1, and point 2, that if I do that on relativistic fluid, I do not get the most generic non-relativistic. This I gave you a very simple, I gave you an example here to show how it fails in thermodynamics. Of course, since it fails at the very first step, if you now try to do hydrodynamics on top of it, it will fail miserably, and that's what we see. If you just follow that and do the calculation, there are problems. Problems, by that I mean you don't get the most generic one, but you get a subclass, some constraint non-Galilean. Okay, so now the point is, so the thing that we understand that relativistic fluid is not going to work. So this point is not problematic, so let me even write so that it stays in your mind. So relativistic theory, null reduction, proper null reduction, giving non-relativistic theory is not the problematic point. Okay? The point that we saw that if I choose some particular relativistic theory, that is relativistic fluid, and I apply this, I do not get the Galilean fluid, generic Galilean fluid. So now the idea is, let's construct a relativistic theory on the null background, and this relativistic theory I'll just give it a name, null fluid, from the scratch. Let's try to write a theory which has on this background, on the particular null background, which has this property that that it has a particular null character. Okay, so relativistic fluid is not going to work. We have understood. Let's try to construct a theory that may work. And the theory that I'll construct, I'll give it a name null fluid, and let's see what is that. Okay, so before I go ahead and tell you, the result is, what I found is that this theory, the null fluid, after null reduction, gives us the most generic theory. Okay, so let's construct it. Let's see what it is. Okay, fine. Okay, so first again, let's go back and try to understand what we are doing. So what we are considering is a manifold, a space-time, where you can assert in matrix, and then we describe a physical theory on this manifold by some dynamical fields. Let's call all of them to be phi. Now this manifold has to, since I intend to do null reduction, so this manifold should have a covariantly constant non-killing vector field, which basically in equations it means that it should kill my metric. The Lie derivative of the metric along that should be 0. It has to be null and it should be covariantly constant. Okay? So now, as we have seen that it can be interpreted, the reduced theory can be interpreted in this theory in 5 dimensions with this isometry can actually be interpreted as a 4-dimensional Galilean manifold, and we call this, let's give it a name. Again, this is not new, people already knew it. Let's give this background a name. Okay, so when I say null background, I mean you have some metric, not just a metric, you have a particular vector field in that satisfies this. Okay? Yeah? Good. Now I want to construct a theory on this background such that my dynamical fields are also invariant by this null direction. I mean, this is also a symmetry direction for this, which means that the derivative of all the fields along that should also be same. Okay? And the result is, I'm first telling you the result, that a physical theory defined on null background, when I say physical theory, I mean the dynamical field satisfying this condition on this null background will be realized as Galilean theory. What do I mean by that? What I mean is this, let's say I have a QFT like in relativistic setup. So basically we know that my dilation of the partition function will be some tensor and dilation of that. Okay? Right? Now if I say that my metric is special, I mean my spacetime is special which has this, then you can actually rewrite, and also the equation of motion just from diffeomorphism invariance is just this. Okay? Now if this metric is, if my spacetime is such that it has an extra vector field V that satisfies all these conditions, and all the dynamical fields, I mean the stress tensor, the stress tensor of the whose stress tensor I'm constructing, if all those fields also satisfy this condition, then you can show that this equation will be equivalent to, you can break this equation into Galilean equations. Okay? I'm not doing it here, it's a little bit of a lengthy process, but that's what one can show just from the picture. So all I'm doing is instead of restricting me to the full symmetry, I am saying not all the diffeomorphisms are allowed now, but only those diffeomorphisms are allowed which does not change my view. If you restrict to that, then that equation will give you the Galilean. So to actually see it more in the language of Galilean fields, what you need to do is to choose a time field as well, because if I want to describe the theory as a Galilean theory, then I need to tell you what is the Galilean time and what are the spaces. So I need another field in my space. So let me call that T. And then this xm, the space-time coordinates, will actually be splitted in x minus t and xi. And you can choose your v to be del minus and t to be del plus. And then the metric actually just splits into this. So here you see that you have now, again my x minus is still a non-direction because I have not allowed all the fluctuations that are allowed here are independent of my x minus, because I want my x minus is nothing but v, because I want everything to be independent of that. I want that symmetry to be intact. So all the fluctuations are independent of that, and that basically requires this kind of conditions on these quantities. And also I want my i's, as I said, to be independent. But if you do this explicitly, then this equation will just give you the equations.
So phi is any other field.
Phi can be anything. So up to this point, I have not specified on any particular physical theory, but I am saying what a physical theory has to satisfy. Okay? And then it is guaranteed that whatever you choose, this phi can be anything. From here, you will just get all the sword identities that will satisfy that this will be changed. But for this process, of course, you need to choose a type, and that is very important.
BTBI, totally arbitrary.
What is totally arbitrary? These are all totally arbitrary. These are like now my background.
Apart from the fact that they are not functions of
X minus. That's the only function.
So these are like the Gaussian gauge fields, BT and BI.
Kind of. They would act as my sources when I eventually try to write the part. Okay. So now again to just tell you, as we have already seen, that if we start with if I choose these fields to be relativistic fluid variables, then of course the equations will work, but that won't give me the right Galilean fluid. So let us try to construct, let us not try to take relativistic fluid variables, but let us try to construct something else. Okay? So let's see. So now, this is what I am constructing, and this is just a name for me. So although I am saying this null fluid, it has nothing to do with fluids. This is some theory with variables this. Okay? So, okay, before I write the variables, let me just say one thing. So now what is this equation? My equation is still this, right? Del m Tmn equals to 0. So I have 5 equations. Now, I knew that my basic problem there was I had one thermodynamic variable less. Okay, so now let's say I want to choose these fields, these phi I, such that 2 of them are my thermodynamic variable. So those 2 are, let me take one of them to be theta and another one of them to be mu. You can give it any different names, but eventually it should be the temperature and mass control potential. So out of this 5 I am taking theta and mu. Then I certainly do not, I have just 3 extra equations, so I can find 3. So the other 3 quantity should be the velocity vector, but now I need 2 conditions on it, because I cannot find all 5 of them. Now what are these conditions? Now, what are these conditions is certainly not sure, not evident at this point. It can be some conditions, but we know that there should be 2 conditions. Okay? Calculation tells you what these conditions should be. If you are interested, I can tell you just after the talk how these conditions are. Okay? But all I am trying to say is that now let's start to describe a theory on my null background such that my variables are 2 scalars and 1 vector with 2 conditions. And all of these guys are independent of my
Sorry, if you could just go back to your last space, I'm not sure if yeah. Now the thing is, just to understand, the extra chemical potential is tied to an extra gauge field.
At this point, this is just a background. Right? Extra chemical potential here, nothing. Extra chemical potential is showing up here.
So is it tied to something in the higher dimensional picture? Or
is it tied? It would be related. So as I said, it is like a chemical potential for some current that will be related to one of these sketch fields.
Okay. So
I mean, which will be sourced by one of these sketch fields. You see it.
Okay, but just that's what I was wondering. But now I imagine that, for example, all the P minus you had was the charge you might have got just from the gauge field tied to the VT. Is that
yes.
not the case? But that was not enough, right? In that, or rather, varying that was not. It was not possible to vary it independently.
It was not possible to vary it.
But now that you
yes.
keep PT, you will be able to do it.
No, see up to.
Or maybe I should just.
No. I'll tell you. See, up to this point, it is just null background. This is what you had even in that case and even in this case. The new ingredient is here.
So you have an extra.
I have an extra field in my picture.
Okay,
So the new theory that I am trying.
That's what it seemed like, because if you just started with that theory.
Yes. So up to this point, it is just the background. I started with this background there.
You keep an extra field.
Yeah. So, but now the theory that I want to describe is something that has an extra field. Okay, am I going too slow?
No, you're fine.
Fine?
I mean, it's been less than an hour.
Okay. Okay, fine.
Yes.
Okay. So now if this is, so let's now say that these are my variables, and then again write the member for stress tensor for this thing. See, now there is a point. Now everything I should allow every possible terms here that are allowed by symmetry. And now in the background I not just only have the matrix, but I also have a V field. I also have an extra vector. So that's the most crucial point. The most crucial point is this construction, that my stress tensor now can have the usual UN thing, but it can also have a V. It can have metric, but these terms are the new terms.
So this is a kind of stress tensor that would not result from the reduction of a relativistic stress tensor.
Cannot be, because you don't have this. So the variation from relativistic fluid is this. It's a theory whose stress tensor differs from the relativistic fluid by this term and this term. Okay, this is the P, nothing new, but this is a completely new term. Okay. Fine. And all the quantities now can actually vary can be functions of two variables. So again, you demand that there is some entropy current through divergence has to be positive definite, and that will relate this quantity with this through exactly in this manner. And I achieved, somehow it seems that I have achieved now, because this is exactly the thermodynamics of a Galilean system. And so I am now being able to start with a relativistic system. It is not really relativistic in the sense that the fluctuations cannot be functions of all quantities, so it is not invariant and the most generic diffeomorphism invariance that a relativistic theory should have, but it is a restricted diffeomorphism because nothing can depend on my symmetry relations. So it's kind of a symmetry broken phase of a relativistic theory, but what it does is it comes with an extra variable and the stress tensor also changes such that this thing is. Okay. Now after that, so I have constructed the theory. All we need to do is now perform the null reduction on it and see what we get. But at least one point I have been able to show is that this is the problem that I showed you is solved. I already got it. So now if you go ahead and do the calculation, do a straightforward reduction, again you can match the non-relativistic quantities with the relativistic quantities and things works out fine. So there is basically at this level, at the ideal level, there is no need of an identification. The constitutive relations will exactly be in the Galilean form. The thermodynamics works perfectly fine. Thermodynamic variables are now functions of two quantities. And the conclusion is at this level.
R, just to understand, is the new charge, is it, that you get? You have one independent new charge, right? It seems to be
R was even there. Only problem was R was not independent of E and P. Now it is. There was a constant relation. R is now independent.
So in a sense, it's an independent.
It's an independent. Okay, so basically, I have not done anything. I tried to understand the problem that relativistic fluid had and tried to solve it. The way I solved it is first by introducing a new field, but in that process, my equations are fixed. So if I am introducing a new thermodynamic field, then this tells me that I cannot have 4 independent components in the velocity. So velocity components are now 3. That's fine. The lower dimensional non-relativistic fluid should have V1, V2, and V3, not 4. That's good for me. And other thing I did was I understood that my background is not just metric, but it also has a preferred direction. If I want to perform null reduction, then it's not just the metric, but metric with a key.
Instead of, as you are saying, because you're going to do the KK reduction on that direction, you know that you are allowed to break the full Lorentz symmetry, right? Because you're compactifying one direction anyway.
Yes.
So, given that fact, we can have a gauge field or allow the system to have some charge in that direction.
That is what it is.
That's what it is, right? If I understand. I mean, this extra scalar, in a sense, is just...
So what you were saying is this?
Yeah.
Yes, that's fine.
As long as we allow that chemical potential to be independent, then it's good enough.
Yes, so let me go ahead and so all I'm trying to say is that now when I'm writing this thing, you know, that from the study of relativistic fluid dynamics, we know that you can actually write a partition function that would be just functions of your background quantities. By that I mean all these quantities. If you vary your partition function with respect to these backgrounds, you can find the correct constitutive relation. So all these quantities that are appearing here are variation of partition function which is a function of background with respect to the background. So all these guys are related to you. Okay, but you have to allow terms, right? And now I have this term. So if you allow it and then vary it, you get what it is. Okay, is it okay?
Maybe I can ask a later question. So this, what should I do to, this fluid gravity correspondence that Shiraz does, in which you have the constitutive relation with the U's, and basically, you have black hole, and the black hole has its position, that's one collective coordinate, and it has its size, that's the other collective coordinate. The size becomes temperature field, and location becomes a U field. Okay. Now, is this like a black hole and some condensate?
So now here,
what is it?
Yeah. So now here you need to start with a black hole that will asymptotically, not be ADS, but it will be kind of Lipschitz. Okay, so you have that extra exponent in your. Okay, so if you're asking me, I have not worked out the holographic part yet, but this is how it should come. Because see, here so your question is at this level, is it? So what he was doing is he was using ADS EFT, and then this CFT was being approximated as hydrodynamics. Right? And these equations was coming from the bulk equation. Now all you have to do is some Galilean bulk correspondence, and we know what this guy should be. This should be some black hole which should be asymptotically Lipschitz-like or Schrödinger-like, and then again these equations will turn out to be the right equations. Because I think this part is already done. People have worked out the cousin of ADS CFT correspondence for theories where the boundary is not the relativistic theory but a Galilean.
Where you have these external fields coming in, like
yes, of course. I mean, see, if it is Galilean, no, it has to have that. Okay, I have not worked on it. Yes, but we can certainly talk on it. I thought that should be the idea, but yeah, I have not worked on that yet. Okay, is it clear up to this point? Okay, good. So the conclusion is that the null reduction of a null fluid gives the most generic Galilean fluid, and the map is trivial, at least at this order. That is what I have shown. Now let me go ahead and tell you the proposal. So this proposal is not just words, but we have worked it out. So the statement is null fluid is actually an embedding of Galilean fluid into one space-time higher dimension. You can look at it as a IISER covariant and boost invariant language for Galilean fluids. The mapping is trivial and works to all ordering derivative expansions exactly. To be precise, the null fluid and the Galilean fluid have exactly identical symmetry, identical thermodynamics, identical constitutive relations, and identical partition. Okay, that's the statement. Now, to say more, kind of trying to say why my theory is good. That is, the null theory to me, I find it is very similar to relativistic fluids. If someone, as I was saying, that one can use all the machinery of relativistic fluids to construct the interesting null fluid model, and then can easily understand the structure of Galilean fluids. So the physics is really at the level of Galilean fluids. That is where we understand things. Null fluid is more like just a different language for Galilean fluids, which has exactly everything identical to the Galilean fluid, but technically simpler, and since it is constructed from symmetry, you know the structure. I mean, there is not much of a chance that you can make mistakes over there. Okay, and that is where, okay. So now that's the proposal, and let me tell you the proposal in equations. Okay, what does the statement mean? The statement means basically, so one, as I was saying, that one can write down an equilibrium partition function in terms of the background quantities for null fluid to constrain its dynamics. Okay, before I say so up to this point we have understood that if I want to talk about a certain Galilean system, all I need to do is write a correct null fluid. If I can do that, then getting the Galilean fluid from it is trivial. Good. So now, what can we do there? Because we know that we can actually write the equilibrium partition function in terms of just the background quantities that can actually constrain the dynamics. So it's very easy to constrain the dynamics of null. So every component of the constitutive relation can actually be obtained by the variation of the partition function with respect to the background fields. And then if you do this, then you eventually get this. Okay, so when I say I get this, I basically mean that you need to write here. So the first three terms are just at the leading order, no derivative. Whereas these guys, the EMs and TMNs and RMs are derivative terms. So here you have all the non-trivialities sitting. But you know exactly which terms you can write there because you have a guiding equilibrium partition function to that. Okay, so this is, and once, so step is write the partition function up to whatever derivative level you want to work on, and then write this guy, calculate the TMN from there, and once you have this, then the proposal is just this. So all all the left-hand quantities of, all the things that are appearing on the left side of the equality are the Galilean quantities, and whatever is appearing on the right side are null quantities. So if you know this, from there you can just identify your Galilean currents and Galilean currents. Okay? Yeah? Right? So now what have we achieved by doing all this? First of all, the first thing that I said, that we find a nice trivial mapping between the constitutive relations of a null fluid and a Galilean fluid that works to all order in derivative expansions. That's what I mean for derivative fluid.
You can write a partition function for dissipating.
Equilibrium frame. So you missed this point.
Oh.
So then you need to, I'm not telling you the thing. Then you need to do a frame transformation. But in equilibrium frame, you know what they are. Then you can make your transformation and can get it in whatever frame you want.
For equilibrium configurations.
Yes. Now, the entire null background story can actually be extended to include a slowly varying Parkes torsional spacetime. So your G need not be flat space. It can be any metric which can also have torsion, and that's important. And null background can also, you can also construct the null background where you have some U1 gauge field and you can allow the gauge field to be anomalous. And you can actually do the same thing for non-abelian anomalies and spin anomalies. So I said these last 2 points to highlight because this is what other people have not been able to achieve. So the other way of actually trying to understand Galilean hydrodynamics was to construct Galilean hydrodynamics from it, just from scratch again in the 4 space-time dimensions. So the thing that they were trying to do, I have that comparison with other methods. Okay? So there is a known covariant formulation of Galilean hydrodynamics, and this is done in terms of Newton-Cartan geometries. Maybe some of you know it. And this is done by Jensen in 1408. So what he does is basically this. So this amounts to basically arranging the constitutive relations of a Galilean fluid in a covariant manner and manifests the Galilean diffeomorphism symmetry but not the Galilean boost. However, the analysis is not explicitly Galilean boost invariant, and what he has to do is he needs to construct by hand terms which are Galilean boost invariant. Whenever you need to do something by hand and you go for a complicated system, one actually makes mistake. So then these people actually try to make a construction which is not just Galilean diffeomorphism invariant but also Galilean boost invariant. By what they have to do for this is basically introducing an auxiliary space-time dimension. So the thing that they were trying to do was basically construct the null fluid starting from a Galilean fluid. So it's more like a bottom-up approach of whatever we were doing. So instead, we actually take a more axiomatic quantum view and define a relativistic null fluid in its own right and realize that it is nothing but the Galilean boost invariant representations of Galilean.
So you can get everything that Jensen gets?
Everything. And all sort of anomalies. Now, do I have time?
Sure.
So I just want to show something very. This is again sorry. These 3 slides are technical, but not that difficult. So now let's just think of a background where we not just have gauge field, but also not just a metric, but also a gauge field. Okay. Now the condition is certainly these conditions were there.
Just to ask, for Jensen, he would have had an additional gauge field coupling to his particle number
Yes.
that was not geometrical.
No.
Yes. That you identify with
not geometrical. I would not say not geometrical, but it has some meaning in terms of the Newton-Cartan structure.
But it's coupling to an additional concept.
Yes.
That is not geometrical.
Yes, you are just having it by hand. If you want to, but that's what you have to do. If you want to write Galilean things in a covariant manner, you need to put something. You need to have an extra field. That's what is Newton-Cartan structure. I can tell you what it is. Okay, so now let's do the same thing for charge fluids. Let's do it at the simplest level. These are your equations, and let's just split the equation. Okay, don't look at all the details, but just look at the first equation. This is identical to del T of rho plus del I of rho I equal to whatever quantities. So you can get it, fine. Again, you can do the identification, everything fine, and you can write the equations in terms of Galilean form. Look at the first equation. So the first equation tells you that the mass is actually there is a source for the mass equation. Okay, if I physically realizable theory should be such that at the mass there is no source for mass equations, and that will force me to take AT to 0, which you anyway get by this condition. So let me go back. Slow. I'm saying I'm considering a null background now in presence of a gauge field. So of course the symmetry should A should also have the del B of the D derivative of A along B should be 0, and on top of that you need this condition, and that anyway makes AT to 0. So you get the right equations. Okay. But now what does it do for you? What it does for you is that if you now try to think of a theory where you have some anomaly, where del and Jm is not 0 but something non-trivial, and if you reduce it, if you null reduce it, you see that the right hand side is proportional to T, and so your lower dimensional theory is not anomalous. This is in some sense acceptable, because if I want to start with a relativistic theory with anomaly, it should be defined in even dimension, and by this process the non-relativistic theory that I am getting is anyway in odd dimension, so it's better that it doesn't have anomaly. Okay, so that's what the scenario is. So it says that start with an anomalous relativistic system, you cannot get anomalous non-relativistic system, and if you start with a relativistic theory in odd dimension, then you don't have any anomaly to start with. So of course, if the C is 0, you don't get anything down in this process. Okay, but the question is, why are we even interested in this? So modified even anomaly on null backgrounds. So the question is, do Galilean systems exhibit anomaly? The answer to this question is yes. Okay, this is again just field theory. So this calculation was done by Roost and Backus in 2011, and they showed that they computed the even anomaly for a Galilean system, to be precise, and they were considering a system with ellipse fermions, and they did some path integral calculations in quantum field theory itself, and they showed that it has anomaly.
The Lipschitz background means actually they looked at a Lipschitz space-time.
Yes. And they found out. Okay? So it's not that they are not there. They are there. So you need to somehow you should be able to get it also. And the thing is, in terms of null background, one can actually get it, because you have you can have a very specific vector directions in your background that will such that satisfy this condition, and that will actually give you the exactly the same. So this is how we are able to construct charged Galilean fluids with spin anomaly, and so again this is only possible for null background. So all I'm trying to say is that null background, odd dimensional null background can have this a term like this that will give you anomaly for an even dimensional Galilean. So it's possible.
So to have an anomaly, don't you need massless fields?
Yeah, this is what I was exactly thinking. How do you?
So this is anomaly for the A1 for correspond the background gauge field A, right?
The background gauge field. So just as a more general question,
yes.
Anomalies always seem to arise because of chirality of
yes.
fermions,
yes.
which requires masslessness.
Yes.
So at some fundamental level,
masslessness of the form.
Yeah, and then it's hard to imagine that a massless field could emit a non-rel intensity, because it's moving at the speed of light.
At this level, I would just say that, okay, so since you know the things very well. So when we were writing it for our relativistic fluids also, we saw that we can actually have some terms in the stress tensor, right? Those terms were there, and they were eventually, so our stress tensors and charge current for relativistic fluid allowed for some possibly parity violating terms, such that when we computed del mu J mu was turning out to be non-zero. All I'm trying to tell you here is that we can have such terms for that. And this structure looks exactly similar to what they already found in field theory.
Yeah, I understand.
So now it is the question that you are asking is to understand how they got it in field theory itself.
I mean, to have an example, one example of a field.
But if I understand,
that's
you didn't take mass. You see, there's a difference between taking a massless fermion, say, in a Lifshitz background, or conceptually, that's a different metric. You can have a, for example, I mean, that's just a particular metric, background metric in which you're examining. That's a little different from
Yes, it is completely
a
different.
massive fermion, in flat space.
Yeah, it is different.
So that's why I was asking that. There, maybe for that reason.
Yeah, I know that they have this term from field theory. So they got it. All I'm trying to say is that in this calculation you can see that there is a possibility of such terms so that this thing is non-zero. And then one way to interpret it is through some anomaly. And such anomaly is exactly the same contribution they found. So they do have, I mean, the statement is a theory with Lipschitz fermions, that is Galilean, has
So just as a statement of field theory, if you had a field theory in, say, flat space with massive fields, can you get an anomaly? Can you get an
If your fundamental fields are massive,
fundamental-
can spontaneous symmetry breaking somehow? This is something I've never. Can it be that we had a chiral field
a spontaneous breaking of the chiral symmetry.
of something? I was just wondering whether is it ever possible that even though your fundamental fields had some chirality, there's a mass gap in it?
Yeah, it's possible. So we have done that kind of a calculation in which we took a Lipschitz theory with Z equal to 3, and this is like a Gross-Nebo model in 4 dimensions, okay, which is possible now with Lipschitz. With Lipschitz kind of thing, that becomes the quartic fermion becomes a marginal term. So anyway, for that you can have a dynamical mass generation, and you can also have a Eumann anomaly. Because the fundamentally the fermions are massless.
Okay.
So you can couple that to some background gauge field, and you will get some Eumann anomaly. And eventually the mass will appear because of like in QCD. So, but fundamentally it is massless.
So usually the way it works is if you have an underlying theory which has chiral representations and therefore an anomaly, and then you go to low energies, then Troft anomaly matching must work, and that either means you have Goldstone bosons which saturated, or you have you have a composite massless.
Yeah, you're saying anomaly matching should make it impossible.
Yeah, it should make it impossible. So it has to. There is, I mean, in the low energy theory, you either have massless fermion, which could be composite, or you have massless bosons whose origin is boson. So,
And the massless bosons will have like a Wechsumino-Witten term or something.
Something like that, exactly.
Yeah.
so
But these
so
statements
either
are
one
true.
or the other.
These statements are true for any background. If your background is not flat, then also this is true.
No. So what I'm saying is, Shiraz's question was, if you were interested in flat background, non-relativistic systems, can you get an anomaly?
No.
Right? And the answer there at least is that. I don't know.
In terms of the fermion language,
No, just as a physical thing, if you have an anomaly, it should never be that you don't have massless.
Yes.
Sounds like anything.
That's
I mean, you
what
can
we
make
have.
it precise because you can look at the triangle diagram and you can cut it. That's Troft anomaly. Okay.
So now let me come to the last part. So outlook, what have we achieved? So we have found an exact embedding of Galilean fluid in a symmetry broken phase of a higher dimensional relativistic system that we call null fluid. The higher dimensional null fluid theory being very similar to relativistic fluid is technically much simpler to handle, and we have found the exact equilibrium partition function for Galilean fluid in that sense, and that can constrain their dynamics on it. And of course, what is left, other than understanding some basics, is I'd be happy if I can really apply it to find all sort of classifications of Galilean transport coefficient in the same way as Yoga and Mukund has done. But this seems more like a technical question, like how to really take. This is more. One needs to really understand the entropy current equation better for that. But the other one is what about the Galilean superfluid?
What about the proof of the equivalence between entropy current, positivity, and the partition?
Yes, that you can
Goes
do.
through.
It goes.
So that
No, yes. but that it is not that trivial. I mean, so first for that, but the first thing that we need to do is basically need to construct null fluid on torsional vector. So the results, the first results that I was showing is for a background where you don't have torsion, because the torsion, once you have the torsion, that again gives you a kind of a current, and that is important to somehow understand the meaning of quantities that you keep on appearing in your calculations. So it is, but yes, as you said, it is more like a technical issue there. I mean, how to extend it.
But once you've shown that there's this equivalence,
yes,
all the constraints come from the partition.
The equivalence works when I take my background to be with torsion.
Okay, fine. So let's take the most general background,
Yes,
that the
then
equivalence works, and then all the constraints that you get come from the equilibrium partition function. So in some sense, that's a classification.
Yes, it is a classification, but you need to do it on null fluid. I understand. That's why I'm saying that this is not really at the level of understanding, but at the level of technicality.
Yeah, we can make it more explicit.
Yeah. Whereas the second one is to what about?
Yeah, that's not really interesting.
That I find is interesting,
Yeah.
because now I need another field.
This Puterman stuff you can clear up even more.
I'm looking at it.
Yeah.
Thank you. Fine.
Yeah, thank you. Very, very clear talk. Questions, comments? Giving it some time to read. It has to be now. Now. Okay. Sorry. Sorry. Will somebody complete the question after the session? Okay. Why don't we take the talk? Anyone who wants?
Karthik, you can.
Yeah. Karthik, would you mind conducting question answer?
If they have.
Sorry.
No, it's okay.
No questions?
Not about the relativistic, but in general, I mean, what exactly is dissipation in forward tense? J mu s is greater than or equal to 0.
So on equilibrium, for equilibrium configurations, your del mu, J mu s is actually equal to 0.
That is equilibrium.
That is equilibrium.
And
So
what is dissipation?
for dissipation, it should be greater than 0.
Or you can write partition function for del mu J mu equal to 0.
I can write partition function for del mu J mu equal to 0. From there, I can only find the quantities in the constitutive relation that will satisfy this. Then you ask me, then what did you get? You can have terms in your stress tensor, in your constitutive relations, which breaks this, right? For example, the eta term. Eta term breaks it. So for that, so I was saying that you do it in equilibrium frame. So in the equilibrium frame, you get that the equilibrium frame is defined like this, that all my fluid velocities, um, eta and mu m, is same as its equilibrium value. Okay, so let me write mu equilibrium, eta equilibrium, mu equilibrium, no matter where you are going in derivative expansion. So in general, these guys will keep on getting corrections from derivative expansion, but I am choosing a frame. You always have this frame choice in your hand. So I am choosing a frame where I am not changing this. If you do this, then that frame is what I am calling the equilibrium. In that frame, if you do the calculations, you can actually find all. And now if you want to get eta kind of terms, all you need to do is just change from one frame to whatever frame you want. Okay? So I mean, there are detailed discussions in that. So if you do the frame transformation, so equilibrium frame is good because in equilibrium frame you can write things from the partition function. Fine. So I am choosing that frame and getting some information. But I want to construct more terms in my stress tensor, and which are 0 if I calculate them on equilibrium frame. So all you have to do is do a frame transformations, and that you can do properly and get it.
So, another question.
Yes.
You said that even from uncharged fluid you getting terms from like this construction of null fluids and then doing the null reduction, which are different from taking the C goes to infinity.
Yes.
I mean, but the non-relativistic fluid is well known, right? I mean,
Yes. Exactly.
So you can see terms which I cannot obtain by some C goes to infinity. I mean, you know which is correct, right? I mean, either C goes to infinity or the null fluid will be reduced.
What is the Navier-Stokes equation? Navier-Stokes equation is, other than the continuity equation and the energy conservation equation, the other equation is this, right? Del J of some Ei. These are the stress tensor. Now this stress tensor you write for it.
Yeah, I know.
Now how you write it is on you, right? So I'm saying that I will allow all terms in this stress tensor that is governed by symmetry. So the way I will do my reduction, I'll always get this equation being satisfied, because I will write Eij as again something some E times Ui Ei Vj. Let me write V so that you understand that it's for non-relativistic, and then you can have some P times eta ij. Then you write the derivative terms, right? I am saying that I will allow all possible derivative terms here allowed by symmetry. So if I do that, then for me this equation is always satisfied. So this equation doesn't tell me which one you should take and which one you should not take. Nobody tells me that actually. Now if you can give me a model where I can do the calculations in the similar idea of ADS CFT, what is ADS? What is holography doing? Fluid dynamics is telling you what is DNA. Then I am telling you a model, a bulk model, where you can calculate the coefficients. If you give me something like that and then I do the calculation, I might find one of the coefficients to be zero. That is fine. Anything else? Good. Sure.
Thank you.